Okay. First of all, I want to thank everyone for joining us today for our webinar on enabling design engineers to optimize for structures and design for manufacturability. We're going to hold off one more minute to get started. We've got more people registering, and then we'll get going. Okay, we'll get started. Again, I want to thank everyone for attending today's webinar on enabling design engineers to optimize for structures in DFM. Today, I'll be presenting. I'm Ed Chapman, Head of Sales and Marketing for ParaMatters, along with Michael Bagalomni, who's our founder and CTO. So let's get into this. Michael? So a little bit about ParaMatters. Really designed to be a generative design tool that enables design optimization and DFM on any CAD model. It really was designed to be used by design engineers. It's intuitive, very powerful. It is the only tool out there that truly enables designers to go in and put design constraints or manufacturing constraints in their design to optimize for structural integrity and design objective with the knowledge of how the tool or how the part's going to be manufactured. Integrates with all CAD solutions, and again is designed to be able to optimize for various design objectives, materials, and manufacturing process. Next slide. Just an example of some of the results that we're achieving with customers, and I think that's really a testament to the capability of ParaMatters. And what you see in common denominator is weight reduction, time reduction, material reduction, and it's significant. And these are real results generated, automotive, aircraft, different machine technologies, and with good brand name organizations. Next slide. So I want to talk a little bit about how we see the market and why things need to change. First of all, Industry 4.0 is really driving faster time to market, more innovative products. It's a tough competitive landscape, especially given what's going on with COVID. It's really important to be able to innovate fast and reduce costs of development. And knowing that you're probably going to manufacture globally, so having tighter control over that design for manufacturability is becoming more and more critical. Getting design right early, this has always been the case in product development. Having design engineers get the design right as early as possible without having to make modifications downstream because the cost goes up significantly, as well as the time delays. And the big challenge, despite all the effort of trying to connect tools, CAD, CAM tools, they're still disconnected. And there's still a quagmire of data that goes back and forth. 45% of an engineer's time is wasted, not being able to be productive in their current tools because of the back and forth of models, data, and thoughts. Next slide. So you think about all the responsibilities of the design engineer, fit, form, function, getting product performance right. In other words, how is this going to hold up under its operating conditions? Is it going to fatigue too early? Is it going to be able to handle thermal management? Is it going to stress and strain too much? Knowing that you had to think about the manufacturing process early in the design cycle. A lot of ECOs and ECNs are generated once that part hits the manufacturing floor. And this has always been the case where manufacturing is sort of an afterthought. But it's really critical to get that right early in the design cycle. And then now, optimizing design. Lightweighting is a big factor, using different material types as a way to reduce cost. and having the design engineer determine that, okay, what material can I use and how does that drive the manufacturing process? All in an effort to be innovative and reduce costs and reduce time to market. Next slide. So if you look at on the left-hand side here, the traditional design loops that occur between the designer, the analyst, the manufacturing groups. I mean, this still exists today, where there's a conceptual design loop where you're getting the sort of the design concept, which is typically taking an existing design and modifying it. Then, of course, you've got the validation loop where the design engineer has to go to the analyst, and there's a back and forth there. That's really cumbersome, slow, and really there's not a lot of optimization going on there because of that cumbersomeness. Also, the fact that there's fewer analysts and those tools tend to be fairly expensive. Then, of course, you have to typically do a prototype to validate can this be manufactured. And because you haven't really perhaps thought about the manufacturing process early in the cycle, that's where a lot of problems occur, and then you're back to square one. We're in ParaMatters, and what we've done with this generative design optimization with manufacturability constraints. This can all be done in parallel. So you set your design objectives, you pick your material type, and then the tool works with you to figure out the manufacturing constraints, how that's going to impact the design. It does the structural integrity piece all in one loop. Okay, and it can run multiple loops very quickly to do that optimization stream. So you're getting true optimization while considering manufacturability and structural integrity. Next slide. So what's happened now is CAD has become the center of, and the model has become the center of the development process. But because of the limitations of the current CAD tools, you're still having to go further downstream in the development cycle to get the design right. You have to go down to the analyst. He works in a CE here. He or she works in the CE tool, to do the structural integrity piece. The design comes back. Then it's going to go down to manufacturing. You build out the prototype. The design comes back. And so these loops and the fact that the CAD model can't be worked to completion by the design engineer is delaying the development cycles. Where in ParaMatters, we're able to work with the design engineer with one tool to figure out the structural integrity and the manufacturability piece and optimize in a usable, very user-friendly tool. Next slide. So again, to reiterate some of the results that we're achieving in cost reduction, material reduction, weight reduction, time to market, these are all numbers and metrics that have been achieved by our customers. And the fact that really every CAD engineer out there, every design engineer out there should have a copy of CogniCAD. Okay, next slide. So what you're going to see, I'm going to transition this over to Michael. He's actually going to show you the solution. Is the fact that we can do this generative design optimization for performance based on your design objectives, for shape, if you're looking to lightweight or cut material or cut mass, and actually the ability to minimize assembly. So in other words, you can take an assembly and work it to turn into one piece. And Michael's actually going to show you an example of that. Generative was really early designed for the additive manufacturing process, and we've been doing that for quite a while now. But we now have added casting and milling as well. So we're the only solution out there can actually do additive casting and milling as part of the design manufacturing constraints. Of course, we talked about structural integrity, thermal management, vibration management, and we can do reverse engineering as well. Okay. Next slide. So the model that we're going to work on, and this is a real life example that we've developed, where there's design that needs to be redesigned, and the design objectives are to reduce assembly, to lightweight it, to find out the optimal manufacturing process, and come up with a whole new concept potentially. So there's an existing design that that is that we have that has two cameras attached to it. It's a bracket with two cameras on it and a control system. And this is the the design that we're going to try to redesign using CogniCAD. There's three loading scenarios. There's forces from the camera and the control units in the XYZ direction, and we're going to consider CNC and additive as two different manufacturing processes to determine what's the right path for us. And then we're going to show a summary of what the results are at the end. But Michael's going to take you through how easy it is to do this with CogniCAD. So at this point, I'd like to turn over to Michael.
Thank you, Ed. Hello, everybody. You see now that we see CAD assembly. We see a bracket, basically, which consists of two parts, the green one and the red one. And this bracket carries cameras. Actually, it's an example from space industry. Original weight of this part from aluminum, actually pretty massive part, is about 10 kilogram. And what we are going to redesign it, it's clear that first of all, we can consolidate those two parts. You see the blue part is in CAD, which we consolidated and also added what we call non-designed regions. Before going into generative design process, as some of you may know, we want to allow smart algorithms to find the best material distribution. At the same time, we need to preserve the interfaces to ensure that our final part will fit the assembly. So from any CAD system, you export a step file and import it into CogniCAD. And I will walk you through a very simple way of setting up the problem while considering all the design objectives, which Ed mentioned previously. So I will go here directly to our platform. So we imported the same assembly that you saw into our system. On the left-hand side, you can see a tree, and setting up the problem, we have to work on the right-hand side panel, which is very intuitive and easy to use. We build it such that you don't need to be an expert to set up a problem. So let's go through steps to set up a problem. First, we need to add material properties, because the design is driven by physics, meaning we need to apply some laws and material properties. We have a quite rich library of different materials. Currently, the isotropic, and the near future, there will be also anisotropic. We will consider aluminum as a material. If some material doesn't exist in our library, you can always go and edit material properties and change material properties as needed. The next step is to define the design space. We imported an assembly. We need just to classify what is our design space, and we made it intentionally ghosted. This is a boundary where part can live. It cannot exceed this area. And we need to specify what we call these non-design regions, which should be preserved, which should be intact. Basically should not be changed by design process. So it's very simple just to classify and select those objects. Objects which will not be classified as neither design nor non-design will be just ignored. So next step is to define loads. For users who do not know the loading condition, we have this option of using our AI engine, which will figure out based on application what's the typical loading scenario. So you still will be able to find the organic and optimal shape. For users who, in this specific case, we know what the loading conditions. So we have loads in X, Y, and Z directions, and our platform can take into account while designing multiple loading scenario. It can be unlimited number of loading scenario. So typically the way you start, you define load case, you can give it a name. It's either static or vibration. And then we need to specify what we call boundary condition, how part is fixed against movement. So it's clear that part is fixed in ball bearing areas here on the bottom. So by default, once we select the part, they fixed against XYZ orientation. If user wants to apply boundary condition on specific face. You can also select a face and so on, pretty intuitive and easy. There is no need to mesh the model, all done under the hood. So we fixed the platform, and now we have to apply loads. So typically, if we have a camera here and we apply load on, we can either apply load on a single part or several parts simultaneously. And so it's quite easy to apply load scenario like this and apply we have. And we could do just exactly the same with the other parts. So by the way, when you select more than one part, you have this box checked. So it's easy to apply load simultaneously on group of parts. So it's very easy and intuitive to do. And the same we can do with this box. I will just skip and move forward. So we define these three load cases, which basically can be reviewed, loading X, Y, and Z orientations. So we can move forward after defining the load cases. And next step is to define what is our design goal, what we'd like to achieve. So for static load cases, there are two obvious ways of designing. Either we want to design for stiffness or we want to design for lightweighting. So if we select lightweighting here, we want to make, so the goal is to minimize mass. Structure, the part should be structurally sound. So meaning if we have material of yield stress of 230 megapascal, we want to keep stress lower. And based on the applications, user can define per each load case different stress criteria. And last is we are going here into some design controls. First, user can control the feature size, which is very important for manufacturability. So user can define will be the minimum feature size of the final model. If you would like to enforce symmetry constraints, there is a way to apply symmetry. For this specific case, only this symmetry plane makes sense. So we would like to take symmetry constraints into account. So even loads can be non-symmetric. You can still enforce symmetry on our case. And what is very important here is to define the manufacturing constraints. So as you can see, we take into account additive, investment casting, die casting, and milling. So for instance, if we go to milling, there are two options, 3-axis milling or 5-axis milling. And here, designer have to apply some judgment of milling will start with the box of, basically the block of material. We would need to make assumption how block is going to be placed and from which direction tool can access. So for instance, if we assume that that part will be like this and we have to allow tool to access, so we have to define 3 axes of milling. So for instance, if these are directions from where tool can access, so we can define like the 3 axes of milling. If you would like to extend it 5 axes to give more freedom to the algorithm to access and allow material removal, this is a way of doing it for milling. For die casting, this is not a good example for die casting, but just to explain how it works, we need also to make an assumption how part is going to be casted, from which direction the material will be casted, and how we're going to demold the part from the tool. So users would need to define here what we call draw direction or demold. So for instance, if material will be casted like this and we would like to demold part from this orientation. Another option is investment casting, which will very similar to additive manufacturing constraints, but enforcing that no internal cavities are inside, or additive manufacturing process as well. And typically from here, the setup is done. You click design and software is able to generate fully manufacturable design, satisfying all the constraints we defined. And I would like to walk through to show a few results. So for instance, so this is a result for 3-axis milling constraints. You see that there is some constraints of the design in terms of it's not like in additive super organic, still tool can access from many of those directions to remove unnecessary material. So what is also interesting to see that you see kind of like original model with a sharp angle algorithm smart enough to avoid these sharp features, not to have high stress concentrations. Of course, the design is backed by the FEA analysis in each direction, and it includes deformations and also stresses. So we can be sure that part is structurally sound, and if needed, that's all. If it satisfies all the structural constraints, it can be downloaded and sent further to manufacturing. Again, this is for 3-axis milling. This is a design when we consider 5-axis milling. So it have 2 more axes, so you can see that design a little more organic in terms of, there's more freedom to remove material. And also, if you notice, the mass of the 5-axis milling is 4 kilogram, while the mass of 3-axis milling is 4.5 kilograms. So it have more freedom, it have more possibility to remove material, and design is very smooth, nice, and organic. Moving forward, this is a design for with stress constraints, taking additive manufacturing into account. You can see the design is very organic. It has much more freedom, but because there is no way for milling to remove material from all those areas. But this is the advantage of additive manufacturing, of where complexity is free. Also, something very similar that you see that our quite unique stress constraints algorithm for strengths, which are able to remove material in potentially high stressed areas and provide very nice results as well. Of course, including all the structural integrity piece, and you have the validation of the FEA. And it's interesting to see, so this is a design for strengths while we avoid stress concentrations. And this is a design for stiffness, typical compliance, which does have, doesn't understand basically this formulation that material does not need to be located. So there's a lot of freedom of having various designs. So this is a design for additive, for strengths, for stiffness, while this is designed for additive for strengths. And these 2 designs you can see for milling, for strengths as well. And if we would like to go to next slide to summarize what we achieved in this case, and you can see we imported the model back into CAD system. It fits perfectly the assembly. You see that the non-design features, the ball bearing areas that we predefined, they stay intact. They need to be there because the part should be attached to the rest of the assembly. And we get an excellent result here. So if we looked at an original design, which was included 2 parts. 2 parts meaning you need to manufacture 2 parts, you need to assemble them. It's very simple case. We had cases where we could consolidate 5-6 parts of the assembly. Its cost reduction is significant. Mass of the original part was about 10 kilogram, and design of the process that Ed explained previously, where users have to draft shape, analyze typically takes about 2 weeks. While applying our technology, which takes both structural integrity and manufacturing constraint into account. So in milling, we could achieve 55% reduction having 1 part, and design cycle took about 2 hours. Among these 2 hours, was about 30 minutes of CAD work of an engineer, and another 1.5 hours pure computational time of the software. And design, you can see this is what comes out of the software without any manual remodeling and reproduction. For additive, because it's much more free, we could reduce weight even further and CAD enormous, like about almost 80% weight reduction in the same computational time. So you can see that the powerfulness of this technology, which really a design tool. Ed, you want to take it from here?
Yeah, thank you, Michael. Great job with that. I'm sure everyone was amazed at the results. So in summary, if you look at the advantages of CogniCAD, it's the only solution out there that can truly optimize designs for engineering challenges, whether it's lightweighting, material reduction, just design optimization with manufacturing constraints as part of the design objective. Um, Certainly, being able to work with any CAD solution is critical. So this way we integrate right with CAD. We're part of your design workflow. There's no need to change what you're doing today. Just enabling the design engineer to have more power, more knowledge to truly optimize design and to think about and to know about the design for manufacturability, part of the solution. Really easy to use. You saw how simple it was to go in and take a model right in from CAD and to set it up for generating results. And Michael could have gone through that in all of 5 minutes. And then generating results took 2 hours on a fairly complex model. And because of the speed of optimization and the fact that you can change parameters very easily and change material types very easily, you can use materials as a design variable now, which can also impact the way you manufacture the part, can radically reduce weight, can radically reduce costs. So we see this as a very unique solution that has been missing in the product development cycle. So to get started, it's really simple. One, you can buy a license. It's very cost effective, and you can certainly request a quote. Glad to do that. You can let us perform a benchmark. So if there's a model that you'd like to see how it would perform with CogniCAD, we can easily take your CAD model and run a benchmark with design objectives. Or you can send it for a 2-week free trial. As I said, it's an hour of initial introduction training, and you run it for 2 weeks, and you can prove to yourself that the solution really works. So again, hopefully we'll hear from everybody on how to get started. We did have some questions that came in, Michael. If we want to cover that, I think there's mostly for you.
Okay.
One of the questions was, does this work with every CAD system? And I guess, how does it integrate with CAD?
Yeah, I think it's fairly easy. Any CAD system export like neutral format, like step file. There are various CAD systems that have their own proprietary formats, and it becomes kind of difficult in the industry to convert. So the neutral format is step, and our system can read the step file. So yes, so the short answer is yes. Any CAD system can be aligned, can work with CogniCAD.
So Michael, this is a question that we get quite often. Can I use this for FEA analysis as a standalone?
Yeah, of course. Just for audience to understand how generative design technology works, these are basically optimization algorithms which find the best material distribution based on FEA analysis, based on physics. It's not magic here. It's a lot of physics and math. So yes, so we have our own FEA, proprietary FEA technology, and this tool can be used also as FEA analysis. And what is important, if what kind of maybe limitation for many CAD engineers to use traditional FEA tools is that they need to clean geometry, they need to mesh the model, and kind of application of load cases becomes complex. In our system, what is interesting that users operate on geometry, on parts, no need to do any meshing. So it makes the use of our tool as just a FEA analysis tool very easy to use.
Great. Another question, Michael. How do I know the design can be manufactured?
That's a great question. So this is our proprietary technology. Again, I started talking about our smart algorithm optimization algorithms, which take physics, structural integrity as FEA into account. But additionally, we developed our technology is such that it can take geometrical limitations into account as well, along with physical limitations. So our algorithms can understand how to place material, for example, for CNC milling, such that the tool will have an access, and also it takes the tool dimension into account such that part will be manufactured. In additive, there is more freedom, and we work with many additive companies. But now, beyond additive, milling and casting is also possible when some of our customers successfully utilize this technology.
Okay, another question, and this is a good segue. What kind of casting design can you perform?
So two types of casting designs typically performed. First is die casting. I think I mentioned, so actually this is the image showing how the same design can be taken for milling and also for casting. So for casting, I think while my presentation, I presented and I explained basically user have to assume the cast or direction and how we are going to demold the part from the tool. It's clear that this part, you see all the ribs, you can demold it down. So we take die casting constraints into account, but another way to take casting is also what we call investment casting. Investment casting is actually very interesting way of manufacturing, especially complex metal parts. So typically you print 3D print sacrificial part from polymer, which later on you create sandcast mold, melt out the polymer and cast inside aluminum. So this typically it's basically fundamentally two different casting technology, and our solution can take both into account. The investment casting, which is kind of hybrid manufacturing, and also die casting.
Great. Michael, another question came in. This is interesting. Are there any plans for design for manufacturability for metal binder jetting?
Yes. Actually, die casting, while applying die casting constraints, works very well for metal bind jetting due to manufacturing limitation of having support structures and constraints. So actually many of our users utilize milling and die casting technologies having, let's say, more simplified shapes, which yield into more cost-effective designs, even for additive. So, so you see, for additive, we kind of want the lightest possible design. The design sometimes very complex, and post-processing can become cost prohibitive, and hence applying some additional manufacturing constraints work very well for those constraints.
Okay, great. Well, I think that's all we have for today, and we're running a little over time. But Michael, thank you very much, and certainly all attendees, I want to thank you very much for your consideration today. Hopefully, this was informative. I look forward to reaching out to everybody. We will send a copy of today's presentation out to all attendees, and certainly you'll reach out. We can schedule a one-on-one demo for your team, and we're going to certainly do the other follow-ups that we had on the slide. But again, thank you very much, and enjoy the rest of your day.
Thank you. Bye-bye.